Series and parallel circuits. This is a quick review of how we calculate and the different rules involved. All right, so let's get started. First thing we want to look at is, let's look at a series circuit. So here's my series circuit. 1, 2, 3 chunks of resistance. There's my DC source. And everyone knows that with a DC source, the short line indicates a negative, the long line indicates positive, and that means that throughout the entire circuit, we should be able to assign a polarity to every one of our individual loads. It's important that you are able to do that. All right, R1, R2, and R3. Some of the circuit rules for series are, well, first things first, how about current? I total, as in the total current in the circuit, is equal to the current that flows through the first resistor, equal to the current that flows through the second resistor, and equal to the current that flows through the third resistor. I total is equal to I1, I2, and I3. How about total resistance? R total is equal to R1 plus R2 plus R3. And finally, what about the voltage? E total, that would be E, my source, is equal to voltage 1, or R1, plus voltage R2 plus voltage R3. And so if we had a circuit, like in this case, where we have, I don't know, let's say 3 times, let's say 10 ohm resistors, 10 ohms each, that would mean that we need to have a source voltage in there too. Let's say it's 100 volts. 10 ohms each, 100 volts. That means total resistance that I have in this particular circuit is, well, R1 plus R2 plus R3. So R total is equal to 30 ohms because there's 3 of them. If I want to work out the total current would be equal to, well, we need to know a little bit of Ohm's law. So that would be equal to the total voltage divided by the total resistance. So in this situation, it would be 100 volts divided by 30 ohms. So we take 100 divided by 30, and we end up with 3.33 amps worth of current that are flowing throughout the circuit. Now, how many volts are we going to see present across each one of these resistors? Well, the voltage is equal to the current flowing through it multiplied by the resistance. If each one is 10 ohms, that means the voltage of each resistor or across it would be equal to, well, let's use Ohm's law. E is equal to I times R. I total times R. That means that we've got 3.33 times a resistance of 10 ohms, which means, well, 3.33 times 10 gives me 33.3 volts. And that would be for each one of our resistors. Now, what about power? Could we calculate power? Well, we certainly could. Power is actually another additional circuit rule. P total is equal to P1, or power consumed by resistor 1, plus resistor 2 power plus resistor 3 power. So when we look at our power formulas, P is equal to volts times amps, and it's also going to be calculated as current squared times the resistance. If we wanted to work out the power consumed by each one of these resistors, then we could take this formula here, simply because it's easy, and we could then take the voltage of one resistor times the current through one resistor. Well, the voltage across one resistor is 33.33 volts times the current that flows through it of 3.33 amps. So 3.33 times 33.3 gives me 111 watts each. This would be the amount of heat that is being given off by that resistor. So for total power, that would mean that all we need to do is add all of those values together. And since they're all equal, we could take our 111 watts times 3 and give us a total power of 333 watts. Now, this would be for a basic series circuit. What about a parallel circuit? Parallel circuit is going to operate a little bit different. So let's look at those rules. Parallel circuit. Well, parallel circuit is going to have, again, a source. So there's my DC source. And I'm going to sketch in some resistors. 1, 2, 3, all the way back. And again, my source, negative and positive, which means each one of these has a polarity as well. And we're going to name them the same, R1, R2, and R3. In parallel, we have, again, circuit rules. And so in parallel, I total is equal to, well, if we look at the current that flows and then joins at each one of these junctions here, current is going to flow through each one of these. And if we use electron flow theory, that means current's flowing out of the source and then back to the source here. That means that the current that flows through 1 and 2 and 3 must all add together to give me the current down here. And that kind of makes sense, because if you have 1, 2, 3 light bulbs, that's going to draw more current than if you only have 1. So I total is equal to I1 plus IR2 plus IR3. What about the total amount of resistance? R total. Well, there's two different ways for us to calculate this, or to show it, or to use your calculator with. The first one is called the reciprocal method. So that's where we have all fractions. 1 over R1 plus 1 over R2 plus 1 over R3. The other method is called the inverse. And depending on what calculator you have or what you're most familiar with, you'll typically align with one or the other. So the difference is the calculator keys that you're using. So there's two different methods for you to get your calculated R total. Now this is different than in series, right? As you add more resistors in parallel, what happens? If we added another resistor in here, we'd get more current, and more current would then mean Ohm's law, the resistance would have to have gone down. So I always like to use Ohm's law and just have Ohm's law handy when I am interpreting results of a parallel circuit. If you tell me that you've added more resistors, I know the current has gone up. It has to. If the current goes up, that means that the lower portion of this equation, that variable must go down. And that's what we see with our total calculation here. The last one we have is E total. And E total, again, being my source value up here, E total is equal to the voltage across R1 and also equal to the voltage across R2 and R3. So if we wanted to do some calculations with this, what we could do is, again, use the exact same example from the previous circuit. So we take 100 volts, and we could say we have resistors that are 10 ohms each. What I want to work out first is what is the R total. R total is going to be equal to, well, there's 10 ohms each, so we can either do this, 10 negative 1 plus 10 negative 1 plus 10 negative 1, bracket negative 1, or we can do 10 divided by 3. When we do our 10 divided by 3, we end up with a small value of resistance of 3.33 ohms. If we wanted to then use that resistance and calculate the total current, we are using Ohm's law, E total over R total, which means 100 volts divided by 3.33 ohms. So 100 divided by 3.33 ohms gives me 30.03 amps. Now, does that make sense with Kirchhoff's current law and what we have for individual values of current? So 30.03 amps is actually up here. And since each of my resistors is identical in value, they're each 10 ohms, 10 ohms, 10 ohms, that means that they must have the same current flowing through them, which would then lead me to believe that individually their current is very small and it's only about 10 amps. So I, of just one resistor, IR1, is equal to the voltage across one resistor divided by the resistance of that one resistor. That means we've got 100 divided by 10 ohms, which leaves us with approximately 10 amps. So there's always ways to double check. Okay, well, we've done a little bit of current and voltage. What about power? Power. Well, power can be calculated the same way in a parallel circuit. P is equal to E times I. And P is also equal to I squared R, or I squared times R. And so what that means is that we can calculate the amount of power consumed by our resistors with either one of those calculations. Again, just for simplicity, I'm going to use this formula here because it's easy. P equal to, I'm going to work out the power of one resistor, just one. So there, right there, I'm going to work out the power of that one resistor, and that means I need to know the voltage across it and the current flowing through it. Well, the voltage across it is 100 volts, and the current through it, we worked out down here, 10 amps. And so 10 amps, when we multiply them together, 100 volts times 10 amps gives me 1,000 watts. So this would be each, right? Each resistor. And of course, this would be the amount of heat output. Now, if I want to know what the total power was, we would then add them all together. So P1 plus P2 plus P3 would give me the total amount of power. So if we take 1,000, multiply it by 3, we get 3 1,000 watts, and that is the total power. So, what is the equation for calculating total power in a parallel circuit? It's exactly the same as a series circuit. P R1 plus P R2 plus P R3. All three. So, parallel circuits in a nutshell. Series circuits in a nutshell. Parallel and series both have the same power formulas. However, you do need to know the difference in how they're sketched and the correlation of information between each of the diagrams. Let's focus then on Kirchhoff's current law and Kirchhoff's voltage law. Kirchhoff's current law. Current entering must equal current leaving a node. Oh, boy, it's a long sentence. There. Current entering must equal current leaving. And so the significance of that in its most basic form is something like this. Here's a node. And here's a whole bunch of paths of current entering and or leaving. I'm going to say this is 20 amps, 5 amps, 0.5 amps, 3 amps, and what we're left with is one leg right here. How much current on it, and what direction is it traveling? So Kirchhoff's current law states that all the current entering must equal the current that leaves this junction or this node right here. So how many amps are entering? We could do a quick sum. The total amount of current that's entering, well, let's look at all the arrows that are pointing towards my node. So there's my node. 20 and 3 are both entering. So that means I have 23 amps entering the node. How many amps do I have leaving? 5 and 0.5. So that means I've got 5.5 amps. If I know what the entering is and the leaving, and Kirchhoff's current law says they have to be the same, then if I were to subtract one from the other, we end up with a remainder of 17.5 amps. What direction is it traveling on this conductor? Well, entering and leaving have to equal. And so that would mean that the current value has to be leaving in this direction here, right? It has to be leaving. The current would have to be leaving that node, and that current would be 17.5 amps. Now, what about Kirchhoff's voltage law? Kirchhoff's voltage law takes into account our understanding that in a circuit, the voltage values, we should be able to get the sum of them based on where their position is in a circuit. So here's a circuit, and I've got a load, a load, a load, all the way back. And the voltage that we have at different points here is 20 volts, 5 volts, and 40 volts. Kirchhoff's voltage law very basically means voltages in a closed loop equals 0. And so that means the voltage rise must equal the voltage drop. And what we can do with that information is then determine missing voltage values based on what we know to be true within the circuit. So if we look at these 3 loads here that each have a voltage that have been assigned to them, and this one has no voltage and we don't know what the source is, we should be able to use Kirchhoff's voltage law in order to calculate it. So for this missing voltage value here, the 20 volts is from this point to this point. And if we were to go through a closed loop and add the voltages together with their assigned polarities, 20 minus the 5 volts would give me my missing 15 volt drop. Because remember, the voltages here must equal the voltage over here, the voltage rise and drop. 15 and 5 is 20. If we wanted to know what the source voltage was, we could take 40 plus 20, giving me 60 volts, or 40 plus 15 plus 5, giving me 60 volts. Kind of depends on which method you would want to use. So that's a quick summary of some of your level 1 theory.